Hi everybody, I'm David from Fraunhofer IAIS in Bonn in Germany, and today I will be presenting one of our latest projects that's generating passwords using various deep learning text generation techniques. We at Fraunhofer need a bunch of research scientists working in many machine learning related fields, and our team, that's Kostadin, Bogdan and I, have worked on many natural language processing tasks. However, applying this to cybersecurity and passwords was a first for us, so we are very excited to share our progress with you today. So in this presentation, we will first be talking very briefly about the password generation task in general. We will then introduce all the models that we applied to the problem and talk about their architectures and their pros and cons in a hopefully comprehensible manner. We will then look at some results, both qualitative and quantitative, and try to draw some conclusions for future work. Inspired by some recent papers in the field, we took on the task of password generation. That is, building models that automatically generate a large number, millions or billions, of passwords. These passwords should be novel, that is, they should not already be part of some training data set, and they should be realistic. So they should look like real passwords, and we should be able to use them to recover the hashes of real passwords. There are, of course, already established methods that can be applied to password guessing, like rule-based approaches like Hashcat, or probabilistic models like PCFG and Markov models. And also neural networks have been applied to password data in the recent years. However, we want to introduce two architectures that are, to the best of our knowledge, novel to the field of password generation, and see if these architectures work as well on password data as they do on general text data. And we want to see if these purely data-driven approaches might even give us an edge over the established methods. To begin with the technical part, we want to introduce three different deep learning-based methods of generating data: the generative adversarial network, the variational autoencoder, and the transformer. And we will briefly explain their architectures, which tasks they are most suited for, and how to apply them to password data. The first architecture we introduce is the generative adversarial network. The model is based on two independent components, one generator and one discriminator. The generator takes as input random noise and constructs an artificial data point, in this case a picture of a handwritten digit. The discriminator then takes these artificial data points along some real data from a training data set, which would here be real pictures of handwritten digits, and the discriminator then decides which of these data points are real and which are fake and come from the generator. So at the same time, the discriminator is trained to correctly identify real and fake data points, and the generator is trained to fool the discriminator by generating realistic-looking data from random noise. And after training, we can then just feed random noise to the generator and have it generate any number of realistic-looking data points. So this type of architecture works incredibly well on images. If you have not seen it yet, please check out thispersondoesnotexist.com. It's an amazing demonstration. However, for various technical reasons, it only works medium good on text. And this balance between the generator and the discriminator is always very hard to train. In our work, we implement the solution that inspired our project called PasswordsCon, which is a Wasserstein gun with components built on residual nets. The second architecture we implement is based on autoencoders. So an autoencoder is a quite simple architecture that is based on an encoder and a decoder part. The encoder takes a data point from the training data set and maps it to a compressed, or what we call latent representation, that has smaller dimensionality than the original data point. The decoder then takes this compressed, latent representation and tries to reconstruct the original data point. The goal is to learn this compressed representation that already contains all the necessary information that is needed to reconstruct the original data. An extension of this is the variational autoencoder. In this case, we do not only want to encode data into latent space and decode from latent space to reconstruct the original data, we also want the encoded data points to follow some structure, usually a simple distribution like a standard normal distribution. To generate new data, we can then just sample from the simple distribution and feed it to the decoder, which will reconstruct it into artificial data points. By adding these constraints to the latent space and adding some stochasticity to the encoder and decoder, we can then enforce that similar data points will be mapped to similar regions of the latent space. This later allows us for targeted generation to some extent. For example, we could generate passwords that are all kind of similar to some input string, or we could do smooth interpolations between password candidates. We'll see some examples of that later. Variational autoencoders have always worked quite well for text generation, and the latent variable structure allows for the conditioned generation and interpolation between data points. For our experiments, we implement a variational autoencoder with a convolutional neural net base encoder and decoder. The last architecture I will introduce is the transformer. Transformers have first been applied to machine translation and have in the last couple of years revolutionized the entire natural language processing field, breaking record after record on text-related tasks. The transformer is again an encoder-decoder structure. The special part is that its inner workings are almost entirely based on self-attention. With self-attention, the model reads the entire input sentence at once, and this allows the model to make direct connections between any two parts of a sentence, regardless of distance, which makes it different from, for example, recurrent structures, where a sentence is read word by word by word. In this example, when reconstructing the sentence, the animal didn't cross the street because it was too tired, when processing the word it, the model will learn to focus on the words the animal and not the street, even though the street is closer to the word it than the animal. A recurrent model might, by that point in the generation, have already forgotten about the animal. However, a transformer can pass these long dependencies without any problems. So transformers have become the state-of-the-art for text generation. If you have not seen it in action yet, you can check out talktotransformer.com. These models are able to generate text that captures long dependencies, so they keep in mind what they're talking about over multiple sentences and even paragraphs. However, password data does not really have long dependencies. All the passwords in our dataset are going to be independent from each other. Also, there's no native way to do condition generation, which was easily doable for the autoencoder. For our experiments, we fine-tune a GPT-2 model from OpenAI on password data. So GPT-2 is a language model. That means it was trained on a huge corpus of text data, and at each step in the sequence, it tries to predict the next word. To fine-tune it on password data, we then continue the training on a corpus of successive passwords. For generation, GPT-2 then starts at a prompt, for example, the beginning of a sentence, and tries to continue the sentence by adding word after word. To generate passwords, we therefore, after fine-tuning, just start at a random prompt and let the model write pages and pages of passwords. So there's one more significant difference between the models. Both the GAN and the variational autoencoder work on a character basis. That means, as input, the password is split into a sequence of characters. And during generation, at each step of the generation, the model has to choose out of the vocabulary of maybe 70 characters for the next character to append to the word. What the transformer does is it generates the same sequence of text in less steps. It does so by using a method called byte pair encoding, which adds common substrings of words to the vocabulary. That way, the model can generate large parts of the passwords in just one step. However, the size of the vocabulary it has to choose from increases enormously. This is a trade-off that we want to explore for both the autoencoder and the gun, maybe in future work. So that concludes the technical introduction part of this presentation, and we can now have a look at some results. For the next couple of slides, we have trained all our models on the RockU training dataset, which is quite small, contains around 10 million unique passwords. And first, we want to have a look at some random generated passwords. So here we see a random sample from the passwords in the training dataset and from the generated passwords from the individual models. And what we see is that this generated text, well, definitely does look like passwords. Maybe there are some strings in there that kind of lack structure or just appear to be random numbers, but this behavior is definitely also present in the training dataset if you look on the left column. So the differences between the models become a bit more clear when we print the most commonly generated passwords for each model and the most common passwords in the training dataset. As we can see, the transformer generates a lot of very short words and year numbers, which might even be just single entries in its vocabulary, as we've mentioned before. So the transformer would generate one token and then move on to the next password. We also see that the variational autoencoder really seems to like first names, and that the PasswordsCon seems to follow the distribution of the training dataset the most closely. However, we will have to see if this behavior is ideal if the task is to generate a lot of novel passwords. So before we move on to a quantitative evaluation of all the models, we want to have a look at the mentioned condition generation for the latent variable model that we can do with this variational autoencoder. So what we have here is in each column we have two real passwords on the top and on the bottom, and we encode them into latent space and then interpolate in latent space between the two data points. We then reconstruct each interpolation point, and we see that we get some kind of smooth transition between the two passwords. So we swap out single characters and we add or take away a number, and we smoothly go from the top password to the bottom password, while in between most of these strings still look like real passwords. For the condition generation, we want to generate a bunch of passwords that are close to the string love or contain the substring love somewhere in the middle. For that, we take this string, we encode it into latent space, and then we only sample from a small region around this encoded point. Since this latent structure means that similar data points are encoded in similar regions of the latent space, each of these reconstructions will then be close to the substring love. So with these two applications of the latent variable model, we can do a more targeted generation. So if we have some prior information, like a likely substring of the target password, we can do the password generation more efficiently by making the search space more narrow. So now that we've seen some sample passwords, let's dive into a real quantitative evaluation of our models. How do we evaluate? So we have a given data set of passwords, for example, the RockU leak, the LinkedIn leak, Have I Been Pwned, or any other, and we split this data set into a training and a test split. We then train the models on the 90% training data and then generate 10 to the x passwords and see how many passwords in the test set we can reconstruct. So let's first have a look at the models trained on RockU, evaluated on RockU. We see that both the variational autoencoder and the transformer offer a similar performance. They reconstruct up to 40 to 45% or over 500,000 individual passwords when generating 10 to the 9 passwords. So the PasswordsCon delivers a less impressive but still solid performance, and it reconstructs up to 16% of a test set. This may be due to the fact that the PassWordCon generates less unique passwords in general, which we'll see on the next slide, or maybe it follows the training data distribution a little too closely. So our models have learned, purely from observing a lot of passwords during training time, to generate hundreds of thousands of real passwords that the models have never seen before. Of course, splitting one dataset into training and test data is kind of biased. The passwords in the testing set come from the same source as the passwords in the training set, and therefore will be in some way similar to the passwords observed during training. And this is a situation that is very unlikely to arise in any real-world application. So that is why we also evaluate our models on a completely different dataset than the one it was trained on. Here we evaluate the models trained on RockU on the LinkedIn dataset that consists of around 40 million passwords that were not observed during training. And of course, our models are not the only methods you can use for password guessing. We've already talked a bit about the established methods, which we want to compare here now. So we use Hashcat and John the Ripper to apply certain rule sets to the RockU training dataset. We have a PCFG model and a 3-gram Markov model trained on the RockU training dataset, and the recurrent FLA also trained on the RockU training dataset. Note that the numbers on the top of the table we've taken from the PassWordCon paper. So now with each model we generate 10 to the 9 passwords, or however many are possible with that method and the RockU data, and we see how many hits we have in the LinkedIn test set. So if we compare the numbers on the right side of the table, we can see that our models are definitely comparable to the established methods, both in terms of total hits and in terms of unique generated passwords and hits per generated password. We see that as a big success, especially since our models are trained without any external information on what a password is or how a password should look like. It's a purely data-driven approach. We conclude that the models have not only learned to recreate the structure of passwords in the training dataset, but have learned to generate passwords in a more general manner. So keep in mind that the RockU dataset is quite small. It's around 14 million passwords, and that's 10 million passwords used for training after pre-processing. So the models have generated and matched to the LinkedIn dataset almost as many passwords, novel passwords, as they have ever seen during training. So if we further go and generate maybe 10 to the 10 passwords, or if we train on bigger datasets, we might even increase these numbers. So in conclusion, we have seen how deep learning text generation architectures allow for the generation of diverse and realistic passwords purely after being trained on a rather small dataset of real passwords. We introduced two novel architectures for password generation, the variational autoencoder and the transformer, that improve on previous applications of neural network architectures for password generation, namely PassWordCon and the recurrent FLA. Additionally, we have seen how latent variable models allow for condition generation and interpolation of passwords, which may help in password guessing tasks when there's prior information available. In future work, we plan to train on different and bigger datasets and further tune the architectures to see if we can further increase the recovery performance. We also plan to submit a full paper on this later this year. So to end this presentation, I now only have to thank our sponsors and thank you all for your attention. We hope you found our talk interesting, and if you have any further questions, please don't hesitate to contact us via email or via Twitter. Thank you and goodbye.